Hello everyone, this is question 5. We're going to do question 5. Now take note that we are not allowed to use graphing calculator for the whole set, for the whole of this question 5. So for 5a, before we go through the suggested solution, I want to highlight to some of you who use different approaches from us. There's this group of people who actually let z to be x plus iy and w to be a plus ib, where x, y, a and b are real constants. Okay, it's not that we don't recommend this method, because the nature of this question here do not allow us to use graphing calculator. So therefore, to solve a set of 4 simultaneous equations involving 4 unknown, it could be rather tedious. That explains why some of you use up 2 pages, okay, to solve the set of 4 simultaneous equations. In the end, there are, due to careless mistakes, you got the wrong value of x, y, and a, b. Unfortunately, that takes out some time as well. So if GC is allowed, definitely this method is feasible. You can go ahead. So in this 5a, where calculator is not allowed, we will not recommend you this method at all. So the other method that we want to talk about is the substitution method. That is, you can let w, okay, to be 2 minus iz. So you replace w, complex number w, with 2 minus iz. So how about w conjugate? So there are some of you who replace the conjugate of w with 2 plus iz. That is wrong, because z itself is a complex number. So you cannot simply say that the conjugate w is just changing the sign in 2 minus iz. That is wrong concept. Alright, so what you can do is, okay, let z to be x plus iy. Therefore, w can be 2 minus I x plus iy. So w can be replaced with 2 minus ix minus y squared minus y, because I squared is -1. So -1 times negative sign is plus. So this is what you can do. Alright, so how about w conjugate? So let me regroup the complex number w with all the real parts, which is 2 plus y minus iz. So this is the real part of w. This is the imaginary part of w. So therefore, w conjugate can be replaced with 2 plus y minus, changing the sign, which is of course plus ix. So you can replace the expression of w and w conjugate with this and this in the second equation, and you can solve for the x and y. Now this is another method if you want to use this substitution here. Okay, let us try another substitution. So before we write out the substitution, let's label this equation as 1, this equation as 2. So from equation 1, we could have z equals to 2 minus w over I. So how do we rationalize I in the denominator? Simply by multiplying I to the numerator and the denominator. That will get us negative I. Remember, I squared is -1, 2 minus w. So I can simplify to iw minus 2I. So we will replace z with iw minus 2I in the second equation. So in the second equation, iw minus 2I times w conjugate equals to 2 plus 4I. So we will multiply in w conjugate to iw as well as 2I. Please recall, okay, if we're going to let w to be x plus iy, okay, so obviously w conjugate will be x minus iy. And what happened to the product of W and W conjugate? That will get us, okay, you don't have to work out. It's very obvious. Over A. We are at question 5b now. Please be reminded that we are not allowed to use calculator for the whole of question 5. That includes this 5b as well. So look at part 1. We are asked to express the complex numbers 1 over p squared in the exponential form. So before we express this number in the exponential form, let's look at what we have. So what is p? So p is equals to a plus ib, where a is the real part, which is a positive value. B represents the the imaginary part, which is of negative value. So what does it imply? It implies that this p lies in 4th quadrant. So with p lies in the 4th quadrant, so how do we measure the argument? So the argument p can be found by taking tangent inverse b over a. Now please take note that b is negative, so that was why we are given negative 2 pi over 9. The argument, you should expect the argument to be a negative sign. So what does this info tell us then? It tells us the argument of p. So with the modulus, with the argument p, okay, given, so how can we make use of this information to figure out the exponential form for this complex number? So recap that this r represent the modulus of this complex number 1 over p squared, whereas this theta represent the argument of 1 over p squared. So we have to make use of the properties of modulus and argument to help us to figure out what is the exponential form for this complex number 1 over p squared. So looking at the modulus of 1 over p squared, okay, by applying the properties, the relevant properties of modulus, okay, can be found by taking 1 over square of the modulus p, where else the modulus p is square root a squared plus b squared. So the result in 1 over a squared plus b squared. Where else the argument of 1 over p squared can be found by using the property of argument 1 minus 2 times of argument p. So that will get us, argument 1 is 0 because 1 lies on the real axis, positive real axis, so such argument will give us 0. So the argument p, as we found earlier on, is negative 2 pi over 9. So therefore, argument of 1 over p squared is 4 pi over 9. So with that, we can express this complex number in the exponential form. Don't forget the I in the power of E. For 5b part 2, we are asked to sketch this point P on the Argand diagram, where it is representing the complex number p. The modulus is square root a squared plus b squared. The argument is given as negative 2 pi over 9. Obviously, it's implying that it's in the 4th quadrant. So for point Q, it is representing the complex number 1 over p squared, which we found earlier on. The modulus of such complex number is 1 over a squared plus b squared, and the argument is actually 4 pi over 9. So that implies the complex number is in the 1st quadrant. Okay, beside figuring out which quadrant does this complex number lies in, we need to also consider the distance that these complex numbers are away. How far are they away from the origin? So we are given this information that a squared plus b squared is greater than 1. So definitely what can we conclude from here? We will conclude that 1 over a squared plus b squared must be between 0 to 1. So in other words, I will expect that the distance of point P away from the origin must be further away from, must be longer, must be more than the distance that this point Q is away from the origin. So therefore, when I sketch the Argand diagram, do remember to label the axes. So this is the real axis. This is the imaginary axis. Okay, I will expect the point Q to be nearer to the origin. Okay, where the argument is 4 pi over 9. And point P to be further away from the origin, where the argument is 2 pi over 9. Negative 2 pi over 9. Now, please take note that you are supposed to label the modulus and the argument on the Argand diagram. So the distance from P to the origin is represented by square root a squared plus b squared, where else the distance from point Q to the origin will be 1 over a squared plus b squared. For students who actually sketch point P and point Q to represented by the solid line, you will be penalized because this does not represent the complex number itself. Okay, so it's a point. So I expect to use points to represent the complex number. So to indicate how far is it from the distance origin to the origin, so you can indicate by the dashed line, not solid line. Alright, and another mistake made by students is that they are not aware, they are not aware that the point Q is nearer to the origin as compared to point P to the origin itself because of this information here. Okay, we are finally at the last part of 5B. Now, before we try to show this expression, we need to figure out what is this angle OQP about. So we have to make use of the Argand diagram that we have from part 2. So let me indicate point P and point Q on the Argand diagram and involve the origin as well. So this is your alpha, and we know that this angle here is made up of the argument Q 4 pi over 9 plus 2 pi over 9. Please ignore the negative sign in the argument of complex number P, because the negative sign in the argument just tell us whether it's clockwise or anti-clockwise direction. So the magnitude of this angle QOP will be 6 pi over 9. The lowest term will be 2 pi over 3. So what else we have? We know that the distance, the length of OP, which is the modulus of complex number P, which is square root a squared plus b squared. And we also know the distance OQ, which is 1 over a squared plus b squared. So with this information, how are we supposed to express that? So in the question, they told us to use sine rule, and looking at the approximate sign here, okay, it seems that they want us to find approximation for this cube of modulus P. So somehow we need to involve the modulus of complex number P. And we are also told that this alpha is small. This angle alpha is small. So let's start with using the sine rule. So what are the possible pair of angles and corresponding length that we can use to help us to find this approximation? So we can make use of sine alpha over square root a squared plus b squared equals to sine 2 pi over 3 over PQ. Okay, but it's kind of cumbersome, troublesome that if I were to use this pair of angles and the corresponding length, okay, I have to figure out what's PQ. Is that a need? Because that PQ, would it help me to involve my modulus P? I doubt so. So therefore, we have to try the sine rule on another pair of angles and their corresponding length. So we can consider this. Okay, we can consider, let me use a different color. We can consider sine alpha over the modulus P. Okay, instead of writing square root a squared plus b squared, let's replace that with modulus P, because that is indeed your modulus or complex number P. And we consider this angle here. So this angle can be found by taking pi minus, subtract away the alpha, subtract the 2 pi over 3. That will give us pi over 3 minus alpha over 1 over a squared plus b squared. Now, how is 1 over a squared plus b squared related to modulus P? If you look carefully, okay, well, we can replace, we can replace a squared plus b squared with the square of modulus P, and that help us to involve the term, the expression modulus P itself. So once we rearrange, okay, we will get Q of modulus P equals to sine alpha over sine pi over 3 minus alpha. So this is how we begin our approximation. So again, this angle here is not considered small angle, so we cannot apply the small angle approximation on sine pi over 3 minus alpha directly. So we have to break out the angle. So how are we going to break out the angle? Okay, we will use the compound angle formula that we have from MF26. Okay, and at the same time, let me apply the small angle approximation on sine alpha and cosine alpha, because we are told that alpha is small. So let me write down the approximate sign. Sine alpha is approximate to alpha, and sine pi over 3 will give us the ratio of square root 3 over 2, and cosine alpha approximate to 1 minus alpha square over 2, minus cosine pi over 3 give us half, so sine alpha is alpha. So we will have alpha over, let me simplify the expression, we will have root 3 over 2. Let me pull out the factor, root 3 over 2. Okay, we will have 1 minus alpha over root 3 minus alpha square over 2. So how do we continue from there? So because on the right hand side of the expression, you notice that it's in the polynomial form, where the powers of alpha is in increasing power, in ascending power. So we will think of binomial expansion. We will have to think of a binomial expansion, and you have to recall from the binomial expansions of such terms in the MF26, right? The first term here must be 1. So, well, that constant term is 1. So we can begin our binomial expansion formula, which is 1 plus minus 1, taking this whole thing as the so-called the x in the binomial expansion formula, minus alpha over square root 3, minus alpha square over 2, and dot dot dot. Now, it's enough because we are asked to show to the expression up to the term that involve alpha square. So therefore, let me simplify it. We will get 2 square root 3 alpha, 1 plus alpha over square root 3, plus alpha square over 2, plus dot dot dot. Okay, they will let us multiplying this coefficient, 2 over square root 3 alpha into the expansion, we will get 2 over square root 3 alpha plus, well, 2 over 3 alpha square. Now how about 2 over square root 3 alpha times alpha square over 2 is not needed because we do not need the terms that with power of 3 or more. So therefore, we are able to show to the expression. So a lot of you, there are quite many of you who actually stop the working here because you are uncertain how to proceed from there. And please take note that, you know, you learn about binomial expansion. You cannot just stop there. So by comparing, sometimes it would be good for you to compare, okay, by looking back at the expression that you're supposed to show, compare and ask yourself, how would you proceed from there to get to the expression there? Okay, when you look at the alpha, the power of alpha is in ascending power, and you notice the approximate sign. So it's somehow already telling you that, you know, it's approximation, okay? Okay, we teachers actually wanted to put in this part 4 for y'all to test you whether you are aware that, you know, the approximation in part 3 is actually not a good approximation. But I guess that is too much to ask because of the time that you are, you know, having, and yeah. So anyway, I take a few seconds, think about it. Now let's look at the Argand diagram and this triangle OPQ. Now recall that OP is given by square root a square plus b square, and the distance OQ is 1 over a square plus b square. And earlier on in part 2, when I asked you to sketch point P and point Q on the Argand diagram, right, we wanted you to be aware that the distance, the point Q is actually is nearer to the origin as compared to point P, because we are given a square plus b square greater than 1, so we expect the reciprocal of the reciprocal of a square plus b square to be smaller than 1, but it's still positive. All right, so that explains why point Q is actually nearer to the origin as compared to point P. So looking at this triangle here, angle alpha, okay, the opposite length is square root a square plus b square. Okay, do you think that angle alpha can afford to be small? Okay, because when you look at this triangle here, it looks like OP is bigger, the distance OP is longer than the distance OQ. So in that case, can an angle which his opposite length that is slightly greater, okay, can it afford to be small? Obviously it can be small. All right, so therefore the approximation in part 3 that's obtained is not a good approximation.